this lecture, we are going to start a new unit of the course, the Unit 2, on the topic of basic tools for calculus for functions of several variables. Here we will recall a few basic concepts from calculus and a few special sets that are of fundamental importance to discuss the ideas of calculus and optimization for functions of several variables. Recall that when we think a point x bar as a point of local minimum of a function of one variable, then on the real number line we consider a set of points that are neighboring to the point x bar, and inside this set of neighboring points this function has minimum most value at the point x bar. A collection of points neighboring to the point x bar is called a neighborhood of the point x bar. In addition to the concept of neighborhood of a point in the n-dimensional Euclidean space, we will discuss the concepts of balls, limit point of a set, and interior point of a set. Thereafter, with the help of interior points, we shall define the notion of open set, and with the help of the concept of limit points, we shall define the idea of a closed set. Furthermore, the concepts of bounded set and compact set also will be discussed. Finally, for a given function of several variables, the concepts of level sets and epigraph will be described. Before starting the lecture, let us recall what we have done in the previous lecture. The previous lecture was a detailed discussion on the idea of quadratic forms. Defining the idea of quadratic forms, we got to know how to check definiteness of a given quadratic form or the corresponding symmetric square matrix with the help of three criteria: eigenvalue criterion, minor determinant criterion, and matrix factorization criterion. Towards the end of the previous lecture, we also got to know ideas of linear functions, affine functions, and quadratic functions. Let's start this lecture with the notion of neighborhood of a point, say x bar, in the n-dimensional Euclidean space Rn. Intuitively speaking, a neighborhood of the point x bar is a set of points in Rn where inside the set one can move some amount of distance along every possible direction emanated from the point x bar. That means a set capital S containing the point x bar is a neighborhood of the point x bar if the set capital S contains a small disk centering at the point x bar having radius delta for some delta greater than 0. This disk type region in the R2 plane or a spherical region in the R3 space, that is a collection of points which are not more than this delta distance away from the point x bar, is called a ball. In general, in the Rn space, we define a ball as a collection of points in the Rn space whose distance from the concerned point x bar is not more than some positive constant delta. If we exclude the points on the periphery of this disk or sphere, then we call this set as an open ball. If, however, we consider to include the points on the periphery of the ball, then we call this collection of points whose distances from x bar are less than equal to delta as a closed ball. With the help of this notion of ball, we define a neighborhood of a point x bar in Rn. The definition of a neighborhood, I must give a denotation of this open ball and closed ball. For open ball, we use the notation b x bar delta and for a closed ball we use the notation B bar x bar delta. By a neighborhood of the point x bar, a non-empty subset of Rn containing the point x bar that includes an open ball, say Bx bar delta, for some delta greater than 0. We commonly denote a neighborhood of a given point x bar by the notation capital N x bar. For example, if we consider a point, say this point in the R2 plane, then a triangular region for which x bar is strictly inside this triangle is a neighborhood of the point x bar. For this point, a region, say this region, is a neighborhood of the point x bar. However, corresponding to a point x bar, a region of this type for which x bar is not strictly inside this region is not a neighborhood of the point x bar, because whatsoever ball of small radius centering at the point x bar you consider, that ball is not lying inside the set capital S, and hence this set S is not a neighborhood of the point x bar. Here in defining neighborhood of a point, we have used the notion of a ball, and a ball is defined with the help of the notion of a distance, which is given by here a norm, and we know in Rn space there are variety of norms. We can use any norm over here to define a ball, and with respect to at least one particular norm, the corresponding ball of delta radius must be inside the set capital S. Then only we call capital S a neighborhood of the point x bar. Let us now identify balls of radius say 1 with respect to different norms in the n-dimensional Euclidean space Rn. We recall that while describing the notion of a norm, we have given several examples of norms in Rn. For example, the Lebesgue 1 norm, Lebesgue 2 norm, Lebesgue p norm for some p greater than equals to 1, and also we have given the definition of maximum norm or the infinity norm. With respect to these four norms, let us try to identify balls of radius 1, which we call as unit balls, centering at the origin of Rn space. Here simply we consider R2 space, and in the R2 space let us try to identify unit balls with respect to different norms. Unit ball with respect to the Lebesgue 1 norm is the set of points for which norm 1x is less than 1. If we are talking about open balls, then we will have here less than 1. If we are talking about closed balls, then we will have less than equal to 1 here. So here better let me call open unit balls in R2. When x is in R2, x has two components. Let's suppose x1, x2. Then the definition of Lebesgue 1 norm gives us this set as set of points in R2 for which absolute value of x1 plus absolute value of x2 is less than 1. Geometrically, this set gives us set of points in the R2 space strictly inside this rhomboidal region where these vertices are one unit distance away from origin. With respect to the Lebesgue 2 norm or the Euclidean norm, open unit ball centering at origin in the R2 space is given by norm 2x less than 1, which is equal to the set of points x1, x2 for which x1 square plus x2 square and positive square root of it is less than 1, which obviously gives a a circular region of unit radius centering at origin, excluding the periphery of this disk type region. With respect to the infinity norm, the open unit ball is given by infinity norm of x strictly less than 1, which by the definition of infinity norm is the collection of points in R2 for which maximum of absolute value of x1 and absolute value of x2 is less than 1, which gives a square region with 4 vertices as the points -1, -1, 1, -1, 1, 1 and -1, 1. Now with respect to the P norm, I am keeping here a home task. You try to find out open unit ball centering at origin with respect to the P norms for different values of P's. In specific, you choose a value of P in between 1 and 2 and try to locate the region given by this set on this figure and also take a value of P greater than 2 and locate this region on this figure. I am keeping these two tasks as two home tasks. Here I must mention a fascinating result regarding different norms in the Rn space, which states that in Rn space any pair of norms are equivalent to each other. Norms, that is norm and norm dash. There exist two positive constants a and a dash such that a times norm x dash is less than equal to norm x, which is less than equal to a dash norm dash x for all x in Rn. For a proof of this result, you can look at the proof of the theorem 2.4.5 on page 75 of the book entitled Introductory Functional Analysis with Applications by Erwin Kreyszig. Geometrically, this result states that inside an open ball with respect to a given norm, there exists an open ball with respect to any other norm. For example, in this figure, you can see that inside this rhomboidal region, we can inscribe a circle maybe of radius less than 1, and inside this unit circle, you can inscribe a rhomboidal region. And this fact is true for any chosen. Like if you choose Liebig 1 norm and infinity norm, then you will find that inside a delta 1 radius unit ball with respect to Liebig 1 norm, there exists an open ball with respect to the infinity norm may be of different radius and vice versa. Due to this fascinating result regarding a pair of norms in Rn, we are free to use any norm while defining neighborhood of a point in the Rn space. We will next define the concept of a limit point. A point, say x bar, is said to be a limit point of a set in Rn if every open ball centering at x bar contains a point of the set capital S which is different from the point x bar. That is, if the intersection of every open ball of x bar having any radius deleting the point center of the ball has a non-empty intersection with the set capital S. For example, let us try to identify the set of all limit points of the set S1, which is a circular region excluding the periphery of the circle, which is geometrically the circular region with radius 2. For this region, we notice that any point lying outside the periphery of the circle is not a limit point, because you have at least one ball centering at this point which has empty intersection with the set S1, and therefore any point outside the periphery of the set is not a limit point of the set S1. If we consider any point on the periphery of this region, then we see that whatsoever ball you consider centering at a periphery point, then that ball contains at least one point of the set which is different than the center of this ball, and hence any point which is lying on the periphery of this circle is a limit point of the set S1. For any point inside this circle, we see that whatsoever ball you consider centering at this point, you have at least one point which is different than the center. Therefore, any point which is lying strictly inside this circle is a limit point of the set S1. So accumulately, the set of all limit points of the set S1 is the set of points in R2 which are strictly inside or on the periphery of this circle. Let us consider few more examples to identify their limit points. For example, we take the set of points on this circle, that is norm 2x is equal to 2. For this set, you please try to figure out the set of limit points and verify that the set of all limit points of S2 is identical to the set S2 itself. In the next example, we consider the set of all points which are lying strictly inside this square and on the boundary of the square, but excluding the points on one side of this square. For example, we take the set of all points in R2 where x1 is in between -1 to strictly less than 1 and x2 is lying in between -1 to 1. The set of all limit points of S3 is the set of points in R2 where x1 is lying in between -1 and 1 including 1 and x2 is lying in between -1 to 1. Please try to figure out why. In the fourth example, we consider intersection of few half planes. For example, consider this line of this line, consider this line, and then this side of this line, consider say this line, and this side of the lines, consider this side and say this line, of which this side. Intersection of all these half spaces of these 5 lines will give us this polygonal region, including the periphery of this polygonal region. Then try to find out the set of all limit points of this polygonal region. For example, take the set as the intersection of x1 plus x2 less than equal to 1, x1 minus x2 less than equal to 1, x1 greater than equals to 0, and say one more, x2 greater than equals to say minus half. Try to figure out this region S4 geometrically and then verify that the set of all limit points of S4 is the set S4 itself. Let us take one more example. Say the set of all points in the R2 plane which are on the first quadrant. That is, we take the set given by x1 greater than equals to 0 and x2 greater than equals to 0. Try to figure out that the set of all limit points of S5 is the set S5 itself. Now notice that in finding limit points of all these sets, often I have used a term called periphery point, or a point on the periphery of these 5 sets. These periphery points have a very special mathematical name called boundary point. Mathematically, by a boundary point, we mean the following: that a point, say x bar in Rn, is said to be a boundary point of a subset of Rn, say capital S, if any open ball centering at x bar of any radius contains at least one point of capital S and contains at least one point outside the set capital S. That is, for any delta greater than 0, intersection of this delta radius open ball with S is non-empty, and this delta radius open ball centering at x bar has non-empty intersection with the complement of the set S. For example, in this set S5, you consider any point lying on the positive x1 axis. Then you notice that any open ball of whatsoever small radius contains at least one point of the set S5 and contains at least one point outside the set S5, and therefore this point is a boundary point of the set S5. Similarly, for the set S3, we see that any point on this side is a boundary point. Any point even on any of the other three sides is a boundary point. However, if we consider any point strictly inside this square region, then we notice that we can inscribe an open ball of small radius which lies strictly inside this square region, and hence this ball does not contain any point outside the set S3, and therefore this point is not a boundary point. From this example S3, we see that a boundary point may be or may not be an element of the set. We commonly denote the set of all boundary points of a set capital S by the denotation del S, or simply by BD of S. For example, del S3 of the set S3 is the set of all points in R2 which are lying on the sides of this square. That is, x1 is either 1 or minus 1 and x2 is lying in between minus 1 to 1, or x2 is either 1 or minus 1 and x1 is lying in between minus 1 to 1. Now, with the concept of limit point, we shall define the notion of closed set. By a closed set in Rn, we mean a set capital S which contains every limit point of the set itself. That is, every limit point of S is an element of the set capital S. For example, out of the 5 sets that we have considered during execution of limit points, the set S1 is not a closed set since S1 does not contain the elements on the periphery of the circular region which are limit points of the set S1. Therefore, S1 is not a closed set. Similarly, the set S3 is not a closed set since the set of points on this side of the square contains limit points of the set S3, but these points are not there in the set S3. Therefore, S3 is not a closed set. For the set S2, we notice that S2 contains all of its limit points and therefore S2 is a closed set. Similarly, the set S4 is a closed set. S5 is also a closed set. So we write here that S1 and S3 are not closed, but the sets S2, S4 and S5 are closed sets. Next, we shall define the notion of an open set, for which we require a concept called interior point. For a given set in Rn, a point, say x bar, in the set is said to be an interior point of the set capital S if there exists an open ball centering at x bar, so that that open ball is wholly lying inside the set capital S. That is, if there exists a radius of the ball such that the open ball centering at x bar having radius delta is a subset of the set S. Let us now try to execute the set of all interior points of the 5 sets that we had considered during identification of set of all limit points. For the set S1, to identify the set of all interior points, let us afresh draw the region given by the set S1, which is this circular region, excluding the periphery of this region. In the definition of interior point, we observe that in order to become an interior point of a set S, the concerned point must be an element of the set. So to identify interior points of the set S1, let us now pick any element of the set S1. Let's suppose an element over here that may be very close to the periphery. Whatsoever close this point is to the periphery, as long as this point is inside the set S1, then we notice that there is a distance of this point to the periphery of this circular region. Now consider half of this distance, and with that half of the distance as a radius, we can draw an open ball centering at this point, but still that open ball is wholly lying inside the set S1, and therefore any point in the set S1 is an interior point of the set S1. So the set of all interior points of the set S1 is the set S1 itself. For the set S2, which is geometrically a circle, now in order to identify set of all interior points of the set S2, we pick up any element of the set S2, and then we notice that whatsoever small radius you consider of this open ball can never lie wholly inside the set S2, and therefore S2 does not have any interior point. So the set of all interior points of the set S2 is an empty set. Now let us quickly identify the interior points of the set S3. For S3, any point strictly inside this square region is an interior point. However, the points lying on these boundaries are not interior points, because whatsoever small open ball you consider centering at the points on these 3 sides, that open ball does not wholly lie inside the set S3, and therefore the set of all interior points of S3 cannot include the points on these 3 sides. Hence the set S3 has interior points as the set of all two tuples where x1 is strictly in between -1 and 1 and x2 is also strictly in between -1 and 1. Now for the sets S4 and S5, we can similarly find that any points with this strict inequality over all these four inequalities is an interior point, and any point with strict inequality over here is an interior point of the set S5. So for S4 and S5, the set of all interior points are this set and this set respectively. With the help of the notion of interior point, we shall now define the notion of an open set. By an open set, in Rn we mean a set whose every point of S is an interior point. Here I mention once again that in order to become an interior point, the point x bar must be an element of the concerned set S. However, in order to become a limit point of the set, the point concerned is not necessarily an element of the set capital S. Let us now consider to identify whether these five sets are open or not. For the set S1, we notice that each and every point of the set S1 is an interior point. Therefore, the set S1 is an open set. For S2, we see that none of the points in the set S2 is an interior point. Therefore, S2 is not an open set. For S3, although we have many interior points, but not all the points in S3 are interior points. For example, the points on these three sides are not interior points of the set S3. Therefore, S3 is also not an open set. Similarly, you can find that S4 and S5 are also not open sets. We neatly write out these S1 to S5, these sets open or not. We have found that the set S1 is open, but none of S2, S3, S4 and S5 is open. Now here from the examples of open sets and closed sets, we see that the set S3 is such a set which is neither open nor closed. Now I ask a question here. Can we have some set in Rn which is both open and both closed? First I write here as a note that S3 is neither open nor closed. Now we take two special sets of Rn. Those are the set Rn itself and the empty set. These two are subsets of the space Rn, but we see that all points in Rn are interior point of the set Rn itself, and any point in Rn is a limit point of Rn. Therefore, Rn is both closed and open. For the empty set, the set of all interior points is the empty set itself, because the set does not have any element and no point in Rn is a limit point of the empty set, and therefore this empty set contains all of its possible limit points, and hence this empty set is both open and closed. And interestingly, these two sets are only subsets of Rn that are both open and closed. As a connection between open set and closed set, we have a result that states that a set in Rn is open if and only if the complement of the set is a closed set, and hence as complement of the complement of a set is the set itself, a set is closed if and only if its complement is an open set. So to check a set is open or not, if it is difficult to identify through the notion of interior points, you can consider to identify whether the complement of the set is closed or not. To find a proof of this result, you may please visit the proof of the theorem 2.23 on the page 34 of the famous book entitled Principles of Mathematical Analysis by Walter Rudin. Now I would like to ask a question. Let's suppose we are given two open sets, say G1 and G2. If I take their union, is the union of these two sets is again an open set or not? What about the intersection? And what about if I take an arbitrary collection of open sets, say G alphas, for alpha lying in some index set, say capital lambda, then if I take their union and intersection, whether those union and intersection of arbitrary collections of open sets are going to be an open set or not. And what about the intersection of answers to these questions are as follows, which I shall write out in forms of two notes. The first note is that for any collection of open sets, say G alpha for some index set capital lambda, their union is again an open set, but intersection of an arbitrary collection of open sets may not be open. As a proof of this result, you may please visit the proof of the theorem 2.24 on page 34 of the same famous book by Walter Rudin. For an arbitrary collection of open sets, you consider the sets of intervals of the type minus 1 by n till 1 by n, this open interval, and you take their intersection where n is lying in the set of all natural numbers, and we see that intersection of all these intervals is the intersection of the intervals minus 1 to 1 with the intersection of this open interval minus half to half, and keep on taking smaller sets. You will finally end up with the intersection as the singleton set containing 0. This singleton set is evidently a closed set, and it is not an open set because the only element of this set is not an interior point, and hence intersection of an infinite collection of open sets may not be an open set. However, if I take a finite collection of open sets, then we can prove that intersection of a finite collection of open sets is an open set. Now, regarding intersection and union of arbitrary collections of closed sets, the result is the following, that for any collection of closed sets, say f alpha for some index set capital lambda, their intersection is always a closed set. However, union of infinite collection of closed sets may not be a closed set. As a proof of this result, you may please follow the same theorem 2.24 on page 34 of the book of Walter Rudin. For union of closed sets, you consider union of all closed and bounded intervals of the type from minus 1 plus 1 by n to 1 minus 1 by n, where n is ranging in the set of all natural numbers. Union of all these closed intervals is the open interval minus 1 to 1, which is not a closed set, and hence union of an infinite collection of closed sets may not be a closed set. However, if you take any finite collection of closed sets, their union is always a closed set. Next, I will talk about the notion of a bounded set. By a bounded set in Rn, we mean those subsets of Rn which are geometrically a finite region. A finite region in Rn can be identified by taking maximum possible distance between a pair of points inside the set. You keep on picking pair of elements from the set and take their distance, And finally find maximum possible distance between pair of elements in the set. If maximum possible distance between a pair of elements inside the set is a finite quantity, then geometrically this region is a finite region. A finite region is called a bounded set. Mathematically, a set in Rn is said to be bounded if there exists a maximum distance among all possible distances of any pair of elements, say x and x dash. Now let us try to identify out of those 5 sets which we have considered earlier over here and try to identify whether they are bounded sets. For the set S1, we notice that maximum possible distance between a pair of elements inside the set S is not more than 4. So S1 is a bounded set. Similarly, S2 is also a bounded set. S3 is a bounded set. S4 is also a bounded set. But S5 is not a bounded set. We simply write out this fact that except S5, all the sets S1 to S4 are bounded sets. With the help of this notion of bounded set, we shall now discuss the concept of a compact set. Although the general definition of a compact set is defined by a notion called open cover, we shall not go into details of open cover and their finite subcover and all. We shall seek here the help of a famous theorem called Heine-Borel theorem and take the statement of the Heine-Borel theorem as a definition of a compact set. By a compact set in Rn, we mean a set that is both closed and bounded. Now out of the 5 sets S1, S2 till S5, those we have considered earlier, you just try to collect which are both open, closed and bounded and accordingly find their compactness. You will find that the sets S2 and S4 are compact, but the sets S1, S3 and S5 are not compact. Next, we shall now define 2 special kinds of sets related to a function of several variables. Those are the notions of level sets and epigraph. By a level set of a given function f from Rn to R corresponding to a given level, say C, the level set of level C is the set of all points in Rn for which the value of the function is equal to C. For example, if I consider the function of 2 variables x1 and x2 is equal to x1 square plus 2x2 square, then corresponding to C is equal to say 1. The level set of level 1 for the function f is the set of points in the R2 plane for which x1 square plus 2x2 square is equal to 1, which identifies an ellipse in the R2 plane. Notice that corresponding to a given level C, the level set LC for the function f is identified as follows. That you consider the graph or surface of the function f which is given by say z is equal to f x1 x2 if I am considering the function f is a function of 2 variables, and then consider the plane z is equal to C. The intersection of this plane z equals to C with the surface of z equals to fx gives us a curve on the plane z equals to C. You take the projection, Euclidean projection of this curve in the x1 x2 plane or in the space of the variable of the function. That projected points in the x1 x2 plane or in the space of the variable will give you a collection of points in the variable space of the function f for which you will get the function values at each and every point on this LC as the value C. Here for this example, we notice that corresponding to this expression of f, we get the surface of z is equal to x1 square plus 2x2 square as a paraboloid. Now take the intersection of the surface of the paraboloid with the plane z is equal to 1. You will get the intersection as a curve on the plane z is equal to 1. Now take the Euclidean projection or the vertical projection of this intersection curve over the x1 x2 plane, which is an ellipse, this particular ellipse, and at any point on this ellipse you notice that the function value is equal to the value 1. Now keep on varying the value of C. This plane z equals to 1 will get varied. That means you move up and down this plane, you will keep getting different intersection curve. Take their projection in the x1 x2 plane, you will get different level curves corresponding to different values of C's for the given function. This is how we find level sets of a given function. Next we shall discuss the concept of epigraph of a given function of several variables. By the epigraph of a function of several variables, say a function of n variables, omega is the domain of the real valued function f, we mean the set of all points in Rn plus 1, the tuples x, y's, where x is in the domain of the function f and y is such a real number whose value is greater than or equals to the function value at x. We commonly denote the epigraph of a function f by simply APF, and we notice that APF is a subset of Rn plus 1, and geometrically APF finds the set of all points which are lying above the graph of the function f. For example, if we consider a hypothetical graph, say a function which is defined on this interval in the real number line, and the graph of the function is a graph like, let's suppose this, then APF of this function f is the set of all points in the xy plane which are lying above this graph and also the points on the graph of the function y is equal to fx. This word epigraph, you know, came from the ancient Greek term epigraphy. English equivalence of this AP is on or above, and graphy resembles to graph of a function. By graph of a function, what do we mean? By graph of a function, we mean the set of all points x, y's for which y is equals to fx. And to define epigraph, we need set of all y's for which y value is above the graph. That means y has to be greater than or equals to fx. That is what precisely the definition of epigraph of the function f. For example, if we consider simply, say, epigraph of the function, say x square, where x is lying inside the set of all real numbers, then epigraph of this function is the set of all points in the R2 plane for which y is greater than or equals to x square. It geometrically identifies set of all points above the graph of this parabola and on the graph of this parabola. Y is equals to x square. With this notion of epigraph, I end up the lecture here. In a later lecture, we will prove that a function f is convex if and only if its epigraph is a convex set. In the next lecture, we will consider to discuss the topic of sequence in Rn. By a sequence in Rn, we mean an ordered list of elements in Rn. We will discuss convergence of sequences too, where the notion of limit of a sequence also will be talked. Furthermore, the notions of limit supremum and limit infimum for a given sequence will be discussed. Before I end, let me give you a few more home tasks for your self-analysis. I will give you home tasks in the form of a few questions or problems. The first problem that I would request you to execute is the following, that find the set of all interior points of the set. Say the set of all real numbers which are of the form 1 by m plus minus 1 whole to the power n times 1 upon n, where m and n are both natural numbers. The second problem is to check whether the set of points in the R2 plane which are satisfying x1 square plus x2 square less than 1 and x1 greater than half is a compact set or not. Thereafter, try to find if the set a neighborhood of the point, say 1 and half, and finally try to draw the level sets, let's suppose L1 and L2 of the Rosenbrook function, whose expression is this one. This function is also called Rosenbrook's banana function, because if we compose the level sets of this function around its parabolic valley, then we get a banana shaped region like these curves, where all these curves are level sets of this function. With this, I stop this lecture here. In the next lecture, we shall discuss the notion of a sequence, the convergence of a sequence also will be talked, and the notions of limit supremum and limit infimum will be described. Thank you all for all of your kind attention.